X value.
Is your X values, correct. Your range is your
Y value.
What comes first in the alphabet, domain or range? What comes first in the alphabet, X or Y? X. What comes first in the alphabet, sine or cosine? Cosine. There's a reason why I'm saying that, because you'll be very happy when you remember that for X coordinates and Y coordinates later on. So in this case here, if you look at the graph on the left there, you'll notice that it is going from left to right. It is increasing until it gets to what value? 0. And then what happens at 0, it increases greater, doesn't it? So at 0, something happened. At that domain value, the slope changes. Remember when we had the example last week about prices at movie theaters for certain, like kids' prices, adult prices, senior citizen prices, values change. It's kind of the same idea. It's what we call almost like a sliding scale, if you will. Now, what we're going to do is we're going to take and basically look at something. Now, I chose a very simple graph to start with. F of x equals x, and f of x equals x minus 1. And there's going to be a domain restriction. In this case, where is the domain changing? For what, at what value? 0. At 0. Okay, everybody see that? Because it says that x is less than or equal to 1, we do one graph. When x is greater than 0, we do another graph. When I have a style like this, especially the first day or so, what I like to do is put a kind of an imaginary, lightly sketched vertical line where the domain changes. So what I did in the first hour, and then everybody was kind of like, oh, that's not a bad idea. I just drew a little yellow highlighter line that I know that something funky is going to happen when my graph hits 0. Okay? You okay with that?
Yeah, I get it.
Okay. So on the first graph, it says f of x equals x. Okay, what's your slope? What's your y-intercept? What's your y-intercept for f of x equals x? 0. What's your slope? 1. Okay. So I know that when y, basically remember it's the same thing saying y equals x. When I'm at x, I know that I would start at 0. Oh, but that 0 line is there, that imaginary vertical line, which means I have to look at my domain restrictions. Less than or equal to. Should that be an open or a closed dot at 0? Closed. Good. So I'm just going to make an overly sized closed dot here. And then normally, I would walk my slope. My slope is a positive 1, which means I'd go up and right 1 every time. But, so if I do that, I'm just going to kind of do this the long way first. I just make a bunch of dots to start with. Up and right is the same as down and left, so I make a bunch of dots going the other way. What part do I erase?
To the right of the center.
Correct. I only want to worry about values of x that are less than or equal to 0, which means I don't care about anything to the right of 0, so I can erase all of those values because my graph is just doing that. Oops. My graph is going this way. That's one way to do it. You can fill up the entire board with dots and then go back to where is it restricted? Well, I can't be to the right of 0 because the domain tells me stop it. It has to be everything less than or equal to 0, so I'm going to the left. All my values of x to the left are what are being plotted. Nothing to the right. Okay. Or if you saw that, give me 1 second. Or if you saw that you knew that your domain restriction was already at 0 and you need to go left, just walk your slope that direction. Yes, sir. Mx plus b. What's the coefficient of x? Yeah, the coefficient is 1 because you don't see it. All right, I do the exact same thing for the other graph. The other graph says x minus 1. Well, where does that graph start at? At negative 1. But remember, I'm restricted at 0, so at negative 1, should that be an open or a closed dot? Open. Open. Very good. And now, what direction does this graph have to go?
Up to the right.
Up to the right. So now I just walk my slope of 1.
So I don't have to put dots on every single.
It's not a bad idea to do that. That way it helps you see the whole graph easier.
Yeah.
It just so happens that this case the slope is 1, so you're going to get a ton of dots on there. But there'll be times that our slope's going to be 3. Okay? So you're not going to have as many dots thrown in there. It helps give you proximity. Okay? And that's how that looks. Again, really, all we're doing here, guys, is you're graphing two equations on one line, and you're erasing where it doesn't exist. Okay? Yes, sir?
Will we still do the dotted line?
No, the only thing we worry about for the dotted or the solid is where your domain restriction occurs at. Those for the dotted and the solid will work with the two variable, multivariable inequalities. These you don't have to worry about that. Because you'll notice how it's just one variable is the inequality, so you're just looking at that domain restriction. It's a great question. Someone asked that in first hour too. Thank you for bringing that up. Okay. Does that make sense, guys, so far? Okay, let's try another one. Same idea. Move this up. There. Again, the idea is if you want, put that little lightly shaded vertical line at 1. Okay? That way I know that something funky happens as I get to x equaling 1. So I've got two equations. Yes, sir?
Will we have like where since x is greater than the last x, together than the other one is a different number?
Yeah, I have an example of that here in a little bit.
So is that where it's like scarce?
Yes. Mm-hmm. Yep. Yep. Completely fine. And it's a very easy thing to look at because then you're looking at within a certain what's called boundary. You know, it's just like what are those called? Oh God, what are those called? Compounding inequalities. -2 is less than x, but it's less than 6. There's that range, that domain, that variance there. Yeah. So you have compounding. So we will have compounding inequalities again. Because you're just erasing. What's that? You're just like mumbling something. I'm going, what? So first graph. First graph says 2x minus 1. Where are you starting? Where at minus 1? Is it x or y? Good. -1. My slope is what? 2. So I have to go up 2 over 1. So if I go up 2 over 1, I get to my boundary line of that something funky happens at 1. So this graph only needs to be to the left of 1 because it's got to be less than. So on that little funky vertical line that I drew, do I make that a solid or an open dot? It's going to be solid because it's got the equal, yeah. Now, I'm not going to continue my up and right because the same thing as up and right is down to left. So I'm going to go down 2 over 1, down 2 over 1. And like I said, I really like the idea of just filling out my graph because it gives me a better idea of how things look. And then I do the exact same thing for the second graph. Answer. Mx plus b, slope-intercept form. Okay. Now I have 3x plus 1. Where does that graph start? At +1. So I start at +1, and I have to go up 3 over 1. Now, at that ordered pair, I hit the imaginary vertical line spot. So should that be a solid or an open dot according to our restrictions? Good. It's supposed to be an open dot. So even if you put a little dot here, if you just draw a big circle around it, that's fine. Because you're just counting. And then from there, I know that that graph's going to exist for everything to the right of 1, so I continue with my slope. Yes, sir?
Why would we do an open dot for the second?
See how it's just greater than 1?
Not great.
So when it gets to 1, it's here. But when it's bigger than 1, it jumps into another line. So you remember how we said that, think of the same idea from ages 0 to 3 is free. Kids under 3 eat free. From 3 to 8, you pay your age. And then from 8 to 20, or from 8 till 65 years old, you pay $13. 65 and older, you're back down to $10. So that's the idea of when you get to a certain spot, it changes. Your prices increase or prices decrease. So here I go back up, 1, 2, 3, over 1. And there's my other slope. The easiest way to think of piecewise functions that I can always go back to is pricing at movie theaters, or how they say there are certain price ranges at restaurants for kids. You know, a buffet. Kids eat free, or so on and so on. Oh, yes. Okay? Okay, try another one. Speaking of,
Why is that?
this is the problem you were just asking about. Okay? What's that?
So the function just doesn't exist inside there.
Right. It's just you're looking, this is, again, back to the idea of it being a piece. It's a piece of a function. We're just looking at a specific part of it. This one has boundaries. Okay? The first one says f of x equals 2x plus 1, and that's between the domain of -2 to +6. Okay. And the other one is at -x when it's between -8 and -4. It looks really, really weird for something that goes real quick. That first graph, I know that I'm looking at values 2x plus 1. When I have this parameter style, where it's just within a specific compound, if you will, I might graph the entire thing again and then go back and erase. So let's see, we have 2x plus 1, so I start at +1 up to over 1. And I knew this was going to be over here, so that's why I'm just doing that. Oops. And it looks something like that. Are we okay with that? Now, I only want the x values to be graphed between -2, open, because it's, and 6, open. I'm only graphing between there and there, which means I'm just going to erase those. I'm looking at a chunk of
So I need to go off the graph.
Yeah, this one just so happened to be off the grid. And it happens. It happens all the time. So it's not a big deal. It'll happen.
To get to the positive 6x.
Yeah. Mhm. Same idea with the -x. What's your slope and your y-intercept for y equals -x? Your slope is -1, and your y-intercept is at 0. Slope of -1 means I'm going down and right. But if I'm looking at my restriction, I'm going to be negative. So I'm just going to go the other direction for right now. So I know it's going to be at 0. It's going to do that. I look for -4. -4 is here. Oops. I look for -8. In between those. You always start at your slope-intercept form, and I'm just not worried about those dots. I just help myself there to walk, starting at 0, my slope is negative, so I gotta go up and left to get into that domain. It looks weird, but as you get into it, it's really fast. You're kind of like this. Yeah. Good. Hi, how are you?
How do you know not to go down to be positive?
The reason I know not to go down that way is because this was given to me. If I went and did all that and filled up my whole graph,
It would be positive.
then I would just erase it. No, it'd still be a -x because it's down and right. Down and right is the same thing as up and left.
Yeah.
Okay. But that domain doesn't matter for this function because it's not in that restriction. And that's where this comes from.
Okay.
Maybe not. Let's see here. Let's try to. You guys do this one. You guys try that one.
Calculator.
So something funky happened around 3. So I'll go back and put my line in there. If you use the line, great. If not, it's not a big deal. 3x plus 2 means I start at 2. Slope of 3. I hit my line, so it's going to be a solid here, because it's going the other way. There's one in the back. There's one in the electric one back there. So we're going this way. And then x minus 1 for when it's greater than 3.
On the line.
This one's my open dot.
Yeah.
Good.
I don't know either. I just know that
What's wrong? What's up?
They were testing how you start on that one. I just say
Slope intercept. Slope intercept form, that's the whole idea. The slope intercept form is the slope and the y-intercept. B is always your y-intercept. It's easier to see. I like to do it just so that we can pretend like because you're trying I just want to. Oh, I'm gonna yell at you. My breath and carve features of your paper. And now that it looks like you.
That's just where
You can. But it's here because then you have to make sure you know where to grab it. So it's always there to start your minors. Now, the other style of these, oops, the other style of this that we're going to look at are going to be called what are called step functions. Good job. But we ran out of time in first hour, so we're not going to worry about it with us either, so we'll give them some time. That wasn't that great.
It's like the guy
There are, ladies and gentlemen, on the website, I've already put the PDF file. I would suggest screenshotting it on your Chromebook or on your phone or something like that. That way you've got the 6 problems. You should have 6 graphs left, whether it's on the back side there. We'll use those for now. I think it's 12 through 26. I think those are the numbers. And go through it. Tomorrow what we'll do is we will talk about what are called step functions, as well as some more of how do you write the graphs, or sorry, how do you write the equation given the graph. So don't lose that sheet that you guys got Friday. That back side of that page we'll use for some notes examples of how do you write equations. And then we'll do the step functions, and then we'll probably do absolute value come Wednesday, which is fine. No big deal. I got a little rambunctiously thinking it'd go faster than we are, which is not the end of the world. Hey, 15 Mondays until your final.
What? No.
It's just counting Mondays. You just count Mondays.
Oh yeah.
That also means there's 16 Mondays.
But there's like 17. There's like 17 Fridays. Yeah. Yes, sir. No, what do you got? What's up, man? Sign off. Yes, sir. Guys. Yes. Well, I don't think you can get all 6 of those done in 10 minutes. So you might be able to get 4. No. These. We're gonna start this tomorrow.
Oh, that's the workout stuff that's done. No, it's always done.
There, is that better? So you stop freaking out? Kids these days. Yes. If you were paying attention, you would have heard me say, oh, this is a step function. Oh, we didn't get to this the first hour, so we'll start this tomorrow. No. Did I say that? Did I say that? You just made an angle side out of yourself.
Where is it?
He won. All right. I think what you did is you did 5 halves plus 12 halves instead of both halves. You added them, you did both halves.
I think what happened.
12 halves and 6. Don't make those 6.